Hey, welcome. My name is Jan Mentzel. I work as a lecturer at DAE, and today in this next iteration of the Vault series, I would like to show you a bit why even as an artist, it's quite crucial that you learn a basic understanding of math, and especially much more important that you learn creative ways how to use it. So for the demonstration today, I will be using SideFX Houdini. So Houdini is a tool that has been around for quite a while in the VFX industry, and it's been mostly used for landscapes, particle effects, explosions, all kinds of special effects. But in recent years, it has been adopted more and more also in the games industry to also make terrain for that, or procedural modeling for games as well. So it's a tool that we in our curriculum use quite a bit, and we actually use it also as a tool to teach math to artists. And you can find this online, and that's one reason we like working with it. It's completely for free for non-commercial use. There's a few limitations here and there, like you can't export everything in the same way, you can't render stuff out, but for learning purposes, Houdini Apprentice will give you everything you need. So you can just find this by Googling Houdini Apprentice, and you can pause the video here, and if you want to follow along, just download it, unless you, of course, already have Houdini. So it's an extremely versatile tool, and it's because the way Houdini is structured is data-driven. So it's all working around data and modifying it. So it was a really perfect showcase of why you should know math, right? Because with math, you unlock a whole another level of power. But that's true for a lot of other programs as well. So you will see I have some examples prepared to show you that are, for example, in Unreal Engine. So even there, knowing math is just one extra tool that you can now use to shape the art in the way you want. So I'll go back over quickly to my overview. So why should you know math, right? Why is it important for you? And to illustrate this a bit, I prepared a few slides. We're going to go very quickly to the actual more applied stuff, but I wanted to give you a little bit of an overview, right? Because initially, and we have this from a lot of students that come to our place, and maybe you've seen other schools as well that teach math, even though you think, okay, math, that seems like something that programmers need to know, and that's true, of course, they need to know math. But even as an artist, it's extremely helpful to be able to do those things. And I'll have some examples prepared for you. And really, the key here is that you don't do math for the sake of math, but we use math as a tool that helps us to do certain things. So for example, here, this very first thing I picked is from one of our courses in the second year. And you can see here, and it's a looping GIF, and you can see here in the background, these screens are all actually driven with some shader math. And actually the entire materials in this scene are all set up that with a bit of some basic math, like adding, multiplying, and so on of some color values, you can actually now automatically generate materials in the scene. And this is probably not what you will immediately think of. If you think of math, you will think of, okay, it's just some calculations I have to do, right? Same here, this is a procedural asset. So that's, again, something that we cover in our school as well. But the important thing here, this is in Houdini, one of the prime examples of Houdini's use cases where you can actually make a model, and that model now can be modified in all kinds of ways. And knowing some math can really be helpful to, for example, figure out here, okay, how high does my object have to go away if I actually if I want to make sure my wheels are always on the ground, even though my wheels are shrinking and sizing up and so on, right? And again, it's not about the difficulty of the math, it's about understanding how you can use it and when you can use it to really aid your art. And then the last example, like some particle effects, right? And for those who have worked on Unreal Engine before, they reworked their particle system recently. And since then, the whole math and programming with that is a lot more exposed to the artists as well. And it makes it a lot more powerful, right? So those are a few examples where if you look at those, you will not immediately think of math. And maybe even the people who worked on this might in their head be like, okay, that's not really math. All I'm doing is I'm taking a value and dividing it by 3 because I'm doing this, right? But in the end, it's about getting that comfortable that when you're actually using the math, you don't even feel anymore like you're doing math. You're actually just solving a problem, right? That's the whole goal, and that's what we try to teach to our students, and I will give you a little bit of an idea of this today as well. Important is, we will need to, before we can actually jump in and do something together, we will need a bit of a quick refresher. And that's just, I don't know what kind of levels people watching here will have, right? And we noticed for us that the levels of how comfortable people with math in like the age group of like 15 to 25 and may also older than that, of course, are very, very different. And so I want to make sure that we're going to cover something very, very basic now. But, and that's, we will see this the moment we actually start doing things in Houdini in a node network, things that we take for granted using like more advanced calculators, like what we're going to do now, order of operations, really becomes very important again, because we now have to tell the computer step by step what to do. So if we make a mistake interpreting the formula, we'll actually do something different than what we intend to do. Order of operations, like I mentioned, what is that? Imagine if you have a formula in front of you, right? And if you just put a big formula into Google even, or into your computer, your calculator, like especially if you have like a more fancy one, it will automatically take care of this. It will automatically understand, okay, I have to first do multiplication before I start doing addition and so on, right? But if you do this, what we're going to do now, turning this math into a node network inside of Houdini, we actually have to make sure we do this ourselves. And so I have these grouped here for you. Very important here, we have first always parentheses, and it can be square brackets as well, like usually we use round parentheses. Those always take a priority, and it's pretty much always a good idea that if it's a bit ambiguous, so if you're not sure, like, is this power outside or inside of something and so on, just use extra brackets. Extra brackets never do any harm. If you overdo it, it might make it a bit hard to read maybe. But brackets in general for programming, for math, they're good to have because they make it also much more readable as well. After them, you have power and square root. And you can see here, this is here separated with a line, and here I use the comma. Why? Because these two are equal. So multiplication, division, addition, and subtraction, those are our tiers. So we have like basically this one beats this one, but if I have multiplication and division, it's not that, and sometimes, and especially in English-speaking countries, it's taught with this, I think it's called PEMDAS or PEMDAS, something like that, which is just the abbreviation of this. But what they often teach wrong is that multiplication would beat division. That's not true, and neither does division beat multiplication. If you have two operations like that, it just goes left to right, actually. And then again, ideally, you just use some brackets around it, some parentheses, to make sure that there is no, it's not confusing which one are you supposed to use. But basically, you have to look here. We have, so parentheses is the most important one. After that, we have power and square root. Then we have multiplication, division, and then as a last one, we have addition and subtraction. So you will see in a second why this is important, because this is something most people learn when they're 10, 9, 8 years old. They forget about it again because they start using so much calculators that it's not important anymore. But if you actually have a formula like this, and you have to solve it step by step, for example, on a piece of paper, you have to start respecting these again. So for example, now the question is, okay, where do I start calculating? Do I first calculate? Do I first divide by 7? But that's quite obvious that we can't do that because we don't know what we divide by 7 yet, right? So if you look at this here, what we can think of, and I'll promise we will make good of use of this today. So that's always our goal, is we try to do some math, but, and you will see later, I'll show you what we're gonna do is we will not just do math for the sake of math, but we're actually going to animate a little like hover vehicle, right? So think Star Wars, for example, right? They have these also all kinds of games like Halo. They have these hover vehicles, right? And if you would want to animate this, but you don't want to animate this using keyframes, but you want to animate in a way where you can adjust it. You can make it go more or less, or it can be maybe a bit quicker. It can go further up, or it starts a different position. You can actually do this with some math. And on top of that, you can use some math also to do some flickering lights. So we will actually use this kind of knowledge we look at today to, in the end, do like a real example of something you could do with this that is not just the math itself. So if you look at this now, like what we start with, we can see that we have a whole bunch of them actually that are on the same level. We have here, for example, we see that parentheses beats everything else. So we would start with this, but it doesn't really matter if we start with this or with this because they don't interact with each other yet. So if we actually look at this, technically all three of these start at the same time, right? But if we now, if we continue now comes the big question. Are we going to first do this operation, or are we first doing this operation? Or maybe divide here first by this, but usually, luckily with the square root, it's quite visually clear that this kind of all belongs together. So in our case here, what are we going to do? We have to pick either we do the left here and the middle one, or we're gonna do the operation of the right part in this. And in this case, multiplication beats the subtraction, right? So subtraction is in this tier, multiplication is one higher, which means we would first do the right part. Obviously, we actually should be doing the square root first, but the square root itself actually counts as a set of brackets, right? So after we solve the inner parts, to be able to solve the square roots, we have to solve everything within the square roots, right? So now that we have this, and if this is super obvious for you, great, because it's really not even, I wouldn't even sure if I could consider this math or just calculating, right? But we basically now have this part here solved on the right, whatever that would be. It's like, I don't know, 4 times 6, right? And then we solve this, and then once we have this one done, we can go to the next step. We could then calculate this part, because we have to first solve whatever is under the root. Then we would calculate the root of this, the end result. And then once we have that result, we can now then divide it by 7. And that's how the square root here trumps the division. Yeah? So we then divide in the end the result of the top part by 7. So now that we hopefully made this clear how this is supposed to work, we're going to try to implement the exact same in Houdini. And you will see that it's quite important to think this through, because if you would look at this, you could just paste this into Google and you would get a result from this. But it's very important that you really know which step comes after the other, because that's how we have to lay out our network later as well. Okay, so let's go to Houdini. Okay, so now that we are in Houdini, I want to show you first what the end goal is of our little session today. Just so you understand why we have to learn all that basic math stuff to get to this actual result. So imagine you have this model. You can just find a similar model somewhere online, or you quickly make this in Maya, Blender, whatever or Houdini, whatever your preferred program is. But we basically start with this model here, right? And then you can just simply, what we basically will do is we both add a light flicker here to one of the engines. That could also be just a light somewhere else on the vehicle or so. And we will show you how to make this move as well. So the idea is that if you start here, you can see this hovers up and down now, and you can see this flickering here as well. Right, we will do this later together, so no worries. I'll go over it much more slowly. I just wanted to show you why we need to understand this basic stuff, because if I open this here and you see inside, this is you can see this is basically just some math nodes here, right? And I'll explain also the math theory we'll need for this, which is sine waves. But first, let's start a bit more simple, and let's actually just try to replicate what we just did in the PowerPoint slides in a bit of Houdini code or networks. And so I'll close this file. And so this is, if you open Houdini, this is how it will look like. You can see here, you can see here our viewport. It looks a little bit different than my previous setup, but we can work with it like this today. All I would do is, for now, we don't really need these parameter tabs here. So that we have a bit more space, we can just close all this here. So all these 3 tabs here. What we will need is we can put some nodes inside of here. And you can also see here on the left our result. But what we want to do first is we actually want to just use this formula and get a bit used to doing some math inside of Houdini. So the most important thing for now to start with is we always need some kind of geometry to apply operations to. Later on it will be super straightforward because we want to make our object move, so we will just apply to that object. But in this case now we just need some kind of object. So what we can do is we right click here in this node network view, and you can make a geometry node. And also I'm not going to make the most basic introduction to Houdini. There's lots of videos outside that will explain you how can you make some stuff here. I will mention the most important stuff, but if this is a bit incomplete, the focus is really on the math for today and how to use it to do stuff. So if something is not clear, maybe quickly just open another tutorial to help you out. But I will try to explain as much as possible while we go through it. And if you have any questions, you can always leave them under the video and we will have a look and try to help you out as well. So important is if you want to work with geometry, we always have to first make a geometry subnetwork. And we can call this, for example, math for now or so. So we're just going to do some basic math. And then we need to apply the math to something. Like I mentioned, so to do this, we're gonna make an object, and the most simple one we can make is actually just a sphere. So you can just again right click here and then type sphere, and we get a sphere, and it should show here. And important is this sphere. If you want to get your parameters now, because we deleted this window on the top, you can just press P, and that shows us up for you as well. So if you deleted them like I did here in the beginning, you can just now press P, but it's a little bit smaller and a bit easier to have them next to each other like this, for example. But important to understand is that this sphere here, it's a primitive. What does this mean? If you look at this sphere here, you can see there is no real vertices visible. And why is this? Because it's a single point in space. And you can see this if I switch you over to the geometry spreadsheet. You can see we have one single point here on the coordinates 0, 0, 0. This is basically a mathematical representation where it has a radius of 1. And by having the point in the radius, it's a bit comparable to what a vector graphic would be in Photoshop, where each point now can have basically nearly infinite precision because it can just recalculate where those points have to be based on the formula of a sphere. But so now we have our sphere, and we want to do some math on this. We want to calculate this. What we will use for this is something called an attribute VOP, and it's a way to code in Houdini without actually using any real coding, like coding without typing basically, but it's a node-based coding. So we can just use some nodes, and then they have nodes like we can add two numbers together, we can make a number and so on. The reason we use this instead of real coding is because it's Unreal Engine, for example, has a very similar system called blueprinting. Where all these things we will do today, like for example making a light flicker, actually will translate pretty much one-to-one into Unreal Engine as well. And because coding is a lot harder in Unreal Engine than it is, for example, in Houdini, you will have to learn some proper C++, you will have to install separate programs. In Houdini here, I could just make a bit of like a wrangler, for example, and then instead, so basically I can pick myself all the math we're doing instead of this. You could technically also write this here as something called a vex expression instead of Houdini. But just because it's so similar and we don't really want to only train our students Houdini, but we actually want them to train this way of thinking, this way of working, we went for the attribute VOP, which basically allows you to get used to working with nodes. And you will see in a second why this is important, because again, if I would use the wrangler and I type some code here, we had the example before, right, where we said something like 2 times 3 plus 5. It automatically would understand in which order to do this. If we work in nodes, though, we have to be the ones that lay out the node in the correct order, or the nodes in the correct order. So to continue here now, what we have to do is we have to take our sphere, and we have to plug this output here into the first input of the attribute VOP. So we can just plug this in here, and then we can give this a better name, and we're going to call this math underscore basic formula. It's not so important, but it's just so for us a bit easier to keep track of what we're doing. And then if you have never worked in Houdini, this is going to be probably very overwhelming as well, but Houdini has these flags, and important to understand is that it works in nodes, and so this is the output of this node, would go into the input of this one, and you can keep chaining this together. And you can decide at what point in this chain of operations you want to look. In our case here, you want to move this blue flag called display flag onto this node. This now means if you're modifying something inside of this, to give an example, I could add a color node here. Yeah, and if I add a color node here, and I actually, let me change the color, the color of this here to, let's say, red, for example. So I did change now the color to red, but nothing is changing. And why is that? It's because I do not have yet, I'm not looking at the right node. I'm looking at the step right before we applied the color. So that's one thing very specific to Houdini, because the way it works with these nodes is I can now exactly decide at what point do I look. This seems in the beginning extremely complicated, but actually the way this is built really is what enables Houdini to be so extremely powerful. It's because you have absolute control. I can, for example, just add a color node to this at this point. I could then use that color to do something else with it. You can change the way how these points are placed in your scene and so on, based on all kinds of reasons. So it's a really, really powerful thing. But for now, we will just stick for this demonstration today. We will actually just stick inside of this attribute vault. So you can leave it here on the color, doesn't matter as long as it's behind this, but I'll just move it back on our basic math formula. If I now double click on this, we will jump inside of this attribute vault. And if I press P again, I can get rid of this for now to have a bit more space. And I'll have to explain first what this does. So we have this attribute vault, which I tried to show already. This is just a way of coding. So we have in our node here, something goes in and then something comes out. And we can decide what we will do in between. And you can see here on the left, we have a whole bunch of things that we can have access to. For example, P here stands for position. So we can get the position of all the objects or all the points that we feed into our attribute vault. In our case, it's just a single sphere for now. Right? We can also look here at the velocity of the points, for example, right? And quite important to take note here is that if you look at the position here, this is colored green, and it says this is a vector. While, for example, the h here is colored blue, this is a float, and we also have stuff like ID here, which is an integer. So it's a little bit important. Try to pay a bit of attention keep attention what you're doing. This would be the position. So, for example, what we can do with this, we can say we want to take the position here. We want to use an add node. Just to give you one example what this could do. And then we could add here a constant to it. So a constant is just a number. And then if I press P here, you can get the parameters for this node, right? So, and now I can decide what I want this constant to be. So for example, this could be 1. So what I can do now is I can take the position here and I can add 1 to it. So now I have whatever the position was plus 1 extra. And I could put this out again here as P. And you will see now, by doing so, I actually moved the sphere here diagonally. Why is that? Because I added both 1 to the X, 1 to the Y, and 1 to the Z. And by doing so, I moved it from 0, 0, 0 to 1, 1, 1. So you can see this here. If I go back to my geometry spreadsheet, you can see that our sphere is now at 1, 1, 1. And that's what we will do later to make it move. We will actually start changing the position like so. Right? But I want to go back here now to my scene view. And this was just one example. But at the moment, we don't really care where our... So if I want to delete stuff, I can delete this, but the connection still stays intact here. So if I want to remove this connection, I can just go here and I can cut through this connection by holding the Y key. So the Y looks a little bit like a scissor. So if you think of it, like it gives you the scissor here, then you can click, drag through it, and you can cut this connection, and you will see then it disappears. Yeah, so that's how you can get rid of it. You can also select a line and press delete as well. So now that we have this, hopefully this understanding of this basic setup, this means if you put something into here, into P, we can decide where this goes. We can, for example, go here and we can put a constant again. And important is to understand our constant here is a float. If I put this in here, this is a vector. It doesn't really make sense, right? A vector usually in Houdini is 3 floats, so x, y, and z in this case for the position here. And you can see Houdini is telling you that there's a mistake here by dotting out this line here. This means Houdini is doing something for you. So it's taking your float and it's trying to turn this into a vector. And we can see what it does if you put this here to 1. It actually, again, you could think maybe it just does 1, 0, 0, but it actually turns into 1, 1, 1. So now if we go here into our position, again, we can see that the position of this point number 0 is now at 1 in x, 1 in y, 1 in z. If I put this to 2, you will see it's now at 2, 2, 2. Right? I'll show you later how you can work around this, but for now, all we want to know is we want to see the output of this formula being calculated we're going to set up. So we will see that it will be, the result should be in x, y, and in z at the same time. Right? So let's try to do this. So if you remember, and I'll make quickly a note here for it. So in Houdini, you can also on the top right here, you can add in this notepad, so this little yellow sticky note here. I can add this here quickly, and I'll write in there what our formula was, just in case you forgot. So we wanted the square root of 7 to the power of 2 minus, and then brackets 2 plus 4. Then we said this was multiplied by 2 to the power of 2. And yeah, I cannot do this, but this was initially our square root was written like this, right? And then after this, it had to be divided by 7. So this is basically what we had on the slide before, right? So how can we implement this again? And you can see now it's even more difficult than before. But if you look at this, we said we go from inwards to outwards, and we will respect so we start with the brackets here, for example. So our first thing we want to do is here, we want to do 2 plus 4. So how can we do this? And we basically just what we're trying to do now is we're going to do 2 plus 4. We're doing 2 to the power of 2 and 7 to the power of 2. We will then calculate them in the correct order. So first multiplying them here, then subtracting the multiplication result from this, then doing the square root, and then we're going to divide it by 7. Just to show you something that if you would do this inside, if I quickly just take this over, and we would put this, for example, into Google here. If I just Google this, I'm pretty sure I'll just get a result. Yeah, see, if I just put this in, it just gives me 0.71. So I'm not sure if it's fully did everything correct, but it looks fine to me. We will see. We will see if we get the same result. So let's try to do this though slowly. So we said the first thing is we have to do 2 plus 4. So I'm going to delete this just in case you didn't continue with this. So what we want to do is we want to start also with 2 plus 4. So we need 2 constants. So we can make a constant. And our first constant here, by pressing P, yeah, here pressing P, you can turn this here into a 2. And then we have to add this together with a 4. So we can do 4. Luckily for us, adding, and that's another important rule you have to understand, is like adding 2 and 4 or 4 and 2 does not matter. So if I do 4 plus 2 or 2 plus 4, it's not really important. Because if we now use the add node, you can see we can actually decide which one gets added first and which one gets added second. right? And for adding and multiplication, it doesn't matter. For subtracting and division, it does, right? So we have to be a bit more careful if we do our subtractions that we actually subtract in the correct order as well. And to do this, maybe it's good that we actually add some brackets here to keep this organized. So we can select this here, and we can use this box here. And what we can write here is this is actually nothing more than 2 plus 4. This is a bit overkill in like normal standards, right? Because you can kind of see what's happening here. But just so we don't make this mistake later where we actually accidentally subtract them in the wrong order, we can add it like this. So we can make our little boxes here, and we can move them there, right? So that's also what I had marked before on the slides. The next one we said, technically we're doing all of these at the same time. We're doing also 7 to the power of 2 and 2 to the power of 2, right? Because all of these are, this has to happen before this, and this, the power basically beats the multiplication here, right? So that's important, like the power here trumps the multiplication on the left of it, and that's why this has to happen first and this has to happen first. Yeah. So we can do this. We can make more numbers by doing constants. So we said we need 2 to the power of 2. So what you can do here is you can just do power, and we can either plug this in here. This would then override the exponent. So you can see now we do 2 to the exponent of 2. That would work. Or alternatively, you can also put in 2 in here. What I will do to keep it even more clean, we will not use typing it in here because you don't see what's happening here anymore. If I'm on another node, I have no idea what I'm powering here. So while this is fine if you would make like a model or something, in our case, when we do the math, we want to keep it very visual, right? You can see nicely what's happening. So we're just going to duplicate this node even as well, and then putting it in here. So now we clearly see we're doing 2 to the power of 2. Yeah. And we can add another box around this. So we have 2 to the power of 2. If you want, by the way, you can give these colors even as well. So you can, for example, make these red if you wanted or so, right? But I'll just, yeah, actually we can leave it like that. Maybe we can, then it's also easier to refer to them. It's getting a bit, maybe gonna be a bit difficult to look at in all the colors in the end. But so now we have this one done, and we needed one more. We needed also the 7 to the power of 2, right? So this is a lot of the same stuff at the moment. But this is basically how you can do some simple math in Houdini, and how you can set up some equations. So if you ever find some equation that you need, so maybe you find somebody online posting, you can just solve it like this, right? So then you can, it's often really as simple as understanding that it applies to your problem, and then just, yeah, turning the formula you've seen into a network without making mistakes. So we have now our 7 and our 2. So we again power this. So you can see we have here now 7 to the power of 2. Another box around this, and we can write this out as 7 to the power of 2. And you can see even this, it's very, very simple, right? It's nothing difficult about this, but it's already a little bit more complicated than what we have to do when we, if you would have a calculator or so, we can just type this in. Now we have to connect the correct value. I have to always put the out and the in. We have to make sure we don't flip them by accident, right? Because 2 to the power of 7 is not the same thing as 7 to the power of 2. So now that we have this one done as well, we have all these 3 first ones done. So we have this one done, this one done, and this one done. And then I said in the slides, right, the next step would be to do this step here. It's the multiplication. It's to make sure that we multiply the left side with the right side, because the subtraction would come later only. So what we can do is we can multiply the result of this and the result of this together. So let's find those two. So we have 2 plus 4 and here 2 plus 2, 2 to the power of 2. And we take the result, which is what comes out here and here. So here it's the power, here's the sum. We take these and we just add them together. And again, because we are adding, oh sorry, it's actually not adding, we have to multiply it. Yeah, we have to multiply it. But, so we can delete this and we try again with a multiplication node. And again here, multiplication, the order does not matter. So I can do stuff like this. It's a bit misleading if you look at it from afar, right? So it's better to turn this around. And if you ever make a mistake now, by the way, it's as simple as clicking on this node and you have here 2 inputs and you can just reorder them. So you can just take these and drag them. You can see it's switching here. So you don't have to always recreate your, if you make a little mistake, you can just fix it like that, right? So what we have now done is we now did our 2 plus 4 times 2 to the power of 2. Then we have to do 7 to the power of 2 minus this. So this is minus this result. So to make it maybe a bit more logical for us, we can also add some extra brackets here, right? So we can say we now did this. And actually, I think I forgot a bracket here, and that's probably why the. Let me quickly undo this and let's double check. Ah, no. Okay, never mind. We can. But my brackets need to be here, and you can see like the brackets here in this case. I'm not sure if they really make it more readable. Maybe if we would space it a bit, so it's a bit easier to see. It would be more because we have basically now here bracket opens, then we have close. So you definitely have 3, but you can see that basically this happens first, then what happens is the next bracket, and then only is the one around the square root, right? So which means we have to now do our subtraction. Now the order matters. So we have to do first 7 to the power of 2, which we already did, which was 7 to the power of 2 here. And then we subtract from that. So it has to be the first input. We subtract from this one. Right? So we can move this around here a bit. If you ever need to change your node, the way they run, you can always just alt-click on them. It gives you this little guy. So you can make it a bit more clear by doing this. It's a little bit easier from afar to see that there's an extra rerouting happening here, right? So now this one here, and we can, this basically would be our entire inner bracket solved now. Yeah. Then as a next step, we have to still apply our square root and then divide by 7. So we can just go here and we can make our square root by just typing square root. And you can see there's no inputs because square root is, it's always basically the root of 2, so to say, right? So you can see here we getting in our value, which is basically the result of everything inside of here. And then in the end, we would pull the square root of it, and now we have to still divide by 7. So we have to take this result, and again for the division it matters, so we have to take the result of the square root and then divide it by a constant, and that constant is 7 in our case. So we take this, and then, like I showed in the beginning, what we can do now is we can just simply take this and we can take this result and plug it into our position. And you can see it moves roughly by 1, so that's a pretty good sign. So there seems to be, it seems to be very similar. And you can see we have here 0.7142. So let's check what we had in Google. We had 0.7142 and so on. So we clearly did the same thing as what we initially typed out. But I hope it's clear that this is much more difficult to do this than, especially without making a mistake, right? You see, even I was like nearly actually added by accident and add and so on. So you have to be a bit focused. You have to always keep in mind, like, okay, do I, because to prove my point from before, you can see here now we have 0.71. For subtraction, I cannot change it. Right? If let me change these, you can see all of a sudden I get actually 0 in the end here. So you can see I get here 0.7, and that's probably actually because it becomes negative and then the score doesn't make sense anymore and so on. But like basically important here to remember is if I do subtract and divide, I have to be extremely careful that I plug the nodes in the correct order. And then for the other stuff is I have to be always following, okay, which operation actually has to happen first. And why is this important? Because I will show you in a second how a sine wave graph looks like in math. And we will use the sine wave graph actually to make our vehicle go up and down, and we will use it to make our color flicker. But we have to be able to set up a sine wave inside of a Houdini first, and to do this, you have to understand how this works. So if this isn't clear, if it was too hard, maybe just take a step back and go through it slower again. But yeah, my mouse is sometimes double clicking, by the way, by accident. But so you can see here, we did just like what we said here on the PowerPoint slides. We first went, basically we did this one. We started initially with doing this one. Then we decided, okay, we have to now multiply together. Then we had to subtract the result from the other first step we started with, in the correct order, of course. And then in the end, only we can do first technically the square root and then the divided by 7. Yeah. So it's very important that this is clear. And then if this all makes sense now, I will quickly explain you the math theory, the math background we need, which is sine waves. And then afterwards, we will slowly actually try to implement, much slower than I did now, we will try to implement this actual hovering behavior with a little bit of math instead of just animating it with keyframes. Okay? So I'll go to the slides now. Okay, so let's have a look at the math theory we need for today. So I'm here in this little application that one of my colleagues wrote, and that's what we actually use to teach in our class. It's very nice because I can do some sketches in here and so on, but also more importantly, it's all interactive. And we give this to our students so they can play a bit around in it. And you can see in the week before, we actually, so it's written by Kuhn, in the week before we actually have the unit circle here, and I'm gonna touch upon it very, very quickly. But what is the unit circle? The unit circle is a circle with the radius of 1. So this one would be here radius of 1 in all of them, right? Important to understand is that it takes 360 degrees to go through the whole unit circle, which is the exact same thing as 2 pi. Right? So 2 pi radians. So we can either measure in degree or in radians. Houdini by default, by the way, expects you to work with radians for all the nodes. But it says it in there as well. It says you have to input basically, and it says radians in the beginning. Yeah, but so we basically you can see here where we have our angle, and based on this, we're gonna look at the sine wave. So if this is super unclear for you, and if you haven't had math for a while, it might very well be. There's some extremely great tutorials I can recommend that are on Khan Academy. It's also for students who come to us and they have difficulties with the beginning of math, because our course really, while we repeat all this and we have theory lectures for all of this, our focus is really on how to apply it. So basically, it's very important that you, to get the basic knowledge, that there's other resources online as well. For example, Khan Academy. And if it's difficult for you to understand what I'm explaining, maybe you can have a look at Khan Academy. You can look at Khan Academy at the unit circle first, and also at the sine wave. But so basically, imagine we have this unit circle here again, right? And what we're having is we have our point here, P1, and that point P1 moves over this circle. And what we're now doing is we're making a graph. And what we're graphing is we're always writing down, basically at the bottom, we're writing down the position, like at what angle are we in radians. Yeah. So let's quickly try this. So I can move here this point. And you can see it graphs here always. So we would be here at, for example, now here at the top, we're at, or let's take an easier one, here all the way at the side, we're now at 3.14 radians. How do I know this? Because it happens to be, it's half a circle. One circle is 2 pi, which means this is pi. So it's technically not 3.14, but it's an easy approximation to remember. It's an infinite number, right? or infinitely repeating number, basically. But if we graph this here, if we always basically just if we always mark down here, okay, this is the angle we're putting in here, and this is the height that we get out of it. If we keep doing this, we will see we get this very nice sweeping curve, right? And you can see I can do this here all the way from the beginning, and you can see this is the sine wave. That's the default. This is just the sine of t, for example, the sine of x. It doesn't really matter. Whatever we have here at the bottom, it would be the sine of the value we have here at the bottom plotted against, right? And the result of that plotted against the value put in. And this gives us this wave. Why is this wave so interesting? Because this wave, if we would look here, and I take this piece and I attach it to this side, you can actually see that we kind of get this repeating effect, right? So I could just continue, and I could continue here all the way. So if I quickly sketch this here, you could see I could just continue here, and I could basically, I mean, it's difficult to draw, right? But I could continue this over and over, which means this is like a cyclical motion, a repeating motion, right? Which is great because that's what we need for the animation. We want it to go up and down and just keep going up and down. But we also want our light to just keep flickering on, off all the time, right? So let's have a look. We have some more detailed explanation here, but I just want to show you a bit what we can have a look here. We have a bunch of parameters as well, and that's important. So the default sine of is just sine of x or so, right? But we can do some other stuff as well. We can, for example, horizontally shift it. And horizontal shift, you can see, what does this do? It basically just changes where the sine wave starts. The actual wave itself does not really change at all. So it would be interesting because imagine how could you read this graph as well? This would be the position of our spaceship, the height of our spaceship in time. So you could say, for example, this here is at time 0, our spaceship is here. After pi seconds, our spaceship would be at this height. So it's not like a left to right movement. You actually have to think again of the point. You're just going up and down the whole time, right? But if I now write here the position and here the time, then I get this kind of motion. Because I have this very nice, basically my movement that goes up and down. It kind of slows down towards the top, and that's why we have this curve here. The curve that kind of like decelerates, then stops, then will be at the peak, and then it accelerates again. And then here it decelerates again. So that's why we get this very, very nice, and you will see this in a second, with this very, very smooth motion that also happens to loop into itself, which is perfect for an animation, right? You can see here, this is the pulsation. What does the pulsation do? The pulsation is basically how often that wave repeats. So the higher the pulsation is, the more waves we have, which means one wave is shorter, which is called a period. So the distance from a beginning to another beginning is called a period. And let me make it maybe like the normal one again, like this. So this here would be one period. And the pulsation and the period and also the pulsation and the frequency are disproportionate to it. They're like basically the shorter my pulsation gets, the longer the period, and vice versa. Because one of them measures how long is one, and one of them measures how many can we fit in. And the shorter my wave gets, the more I can fit in 1 second, for example, right? So that's the pulsation, but we will work with the frequency in a second. I'll show what the difference is. It's just one simple adjustment for that. The vertical shift, you can see here, we can move our wave up and down. And we can see, for example, why is this important? Because with the vertical shift and the next value which I have is the amplitude, I can exactly control from which value to which value this wave will go. To give you an example, what we can do here is we can say, okay, let's take our vertical shift and we can move this in a way like so, and I can adjust my amplitude where, while before, maybe you remember, our unit circle was from 1 to -1, right? It was a circle around 0. Now we actually, by offsetting it with a vertical shift and changing the amplitude, I can actually get us to a way where I'm now moving from a bit over 2 to 0. So my spaceship now, if this would be the position of my spaceship, would actually be moving up and down here. Between this, the lowest point would be around 0 and the highest around 2. So I have full control. For example, if I shift this higher up, I can move this out of the screen, right? But basically now my spaceship or hover vehicle would never actually get below 2. And because I can modify this even after I set it up, I can really tweak my animation exactly how I want it. I can, by changing the pulsation, I can make the motion go faster or slower. And with the amplitude, I can make it more extreme or less extreme. And the vertical shift basically sets around which middle value is, and you can actually see the vertical shift is just the, it's basically this here. It's how much is it offset from its original position, which was 0. So it's just like, and that's why it gets added here in the end. And I don't have time to explain it in much more detail than this. So if you come to us, we have much more lectures on this, and you can find online much more lectures. But I just wanted to give you like a bit of a maybe to remind you of that stuff if you already learned it at some point. If you have never heard this before, this is not going to be enough for you to understand this. But basically what is important for you even then to understand is we have all these nice values that really allow us to modulate exactly this wave however we want to do, right? And then let me quickly show you. So basically we have now the important thing is the default period, like I mentioned, is 6.28 or 2 pi, right? The frequency then is derived as 1 over 2 pi. So basically, because what is the idea of the frequency is that we can count how many waves do we have in 1 second, right? And that's why we have to account for this initial 2 pi that our basic sine of our basic sine of t is actually has a period of 6.28. So we have to account for this a bit, and that's why we have this conversion from the frequency and the before we talked here about pulsation. And that's exactly this conversion factor from frequency to pulsation is this 2 pi. So 2 pi f is actually 2 pi f is nothing else than the pulsation. Yeah. But again, it's there's better videos to explain these details than this one. What I want to show though is we can basically modulate this, and even more interesting, what we can also do, of course, we can do stuff like dampening, for example. Right? We can actually change a bit like how this how strong this gets dampened. So we can do all kinds of. This is just a curve. We can change how this behaves as well, right? But I hope this helps a little bit to understand, because what we will implement now together is we will actually try to basically write this formula, put this into nodes, and then by doing so we have now some math that controls if we give it an input value, which is the time, what should the position be of our spaceship? How high should it be, or how low should it be, or what should the color be, right? So let's jump right into Houdini for that. Okay, so we left our Houdini scene something like this. So we had our math here, right, where I'll try to explain what order comes what, and basically what operation comes after the other, and how do you have to make sure with multiplication and subtraction that which one can you change, which one can you not, and so on, right? So all these really basic math rules. But now we actually have a real formula we want to implement, and that is a sine wave that allows us to check or to calculate actually what the height of our object should be at what given time. And we will later on use a little vehicle for that. But for now, we can just use a sphere as a placeholder. And that's the nice thing with the way Houdini's nodes work, that at any moment I can just replace, I can, for example, replace this sphere here, right? We had this sphere, it was here, and then we had some math that moved it to the right. I can just put a box here. Yeah, the way I set it up, it won't work, but I can. So the reason why this doesn't work immediately is because our box, now every single point of the box gets put on the exact same position, which is here. So you can see it still gets moved, it's just that our box gets collapsed. To avoid this, we can just pack this quickly. And you can see now it works. So I can replace this with a sphere, I can replace it with a box. The math here in the end still holds up, right? So we can first implement this now in a new attribute VOP. So you just type a VOP, and we will just try to implement the basic sine wave function. And we can actually use it both to move, we can use it to move an object, but we can also actually use it to define a color as well. And that's the thing with the math. It's the math is universal, right? In the end, you decide what you're going to do with that value that you get out, and you can put that value into a position, but you can also say, okay, that value is actually just a color value, right? So what we can do is we can take a sphere, And for now, we'll just do it with the sphere. And then we can do the same trick I showed here with the packing, where we just pack it and use it, the packed version of our hover vehicle to make sure it doesn't collapse on one spot. So inside, let's rename this maybe quickly to math underscore hover animation. And then inside here, we want to replicate a formula, right? And we discussed this formula before now. I'll quickly go over it again, just in case. So we have our amplitude. That amplitude gets multiplied by the sine of 2 pi times the frequency, multiplied by a variable. In our case, it's the time. And then we can add to this a horizontal shift, and we can add to this a vertical shift. So this is like if you look for like a generalized sine function, something like this, you will find this. So this is the math that we have, right? This is usually how we start our lessons. Okay, we now know the math. Kuhn gives the theory to all the students. And now we know, okay, we know this math is correct. We know it's true, we know this works. But how can we now make use of it? What we can do is first, we're just going to try to put this formula back into nodes. And we know from before that we have to respect brackets, which means here you can see these brackets take priority. And then inside, we know that multiplication trumps the addition here. All these multiplied values here, for those we can just we can do them basically in the same time because they're equal at the equal level. And also important is that multiplication, the order doesn't matter. It doesn't matter if I multiply 2 by pi or pi by 2. So I can actually just multiply these in any order I want. It will always be the same. So what we can see, we actually need time. So how can we get this time? You can actually see that as part of this, all these inputs here from the attribute VOP, the inputs into the VOP, actually are, there's a whole bunch of stuff exposed. One of them is actually the time. So the time is a float value, and you can see it corresponds here with the value here at the bottom. So this is the frame, right? But in our case, we can just use the time here, and the time would be, if I would be at frame 24, I would be at time 1 second. Right? So there's a direct correlation, and you could change your animation frames, basically how many you have per second, and then it would be slightly different. But I think the default is 24 FPS. Right? In the game engine, you would have to see how many, how much your delta time is, for example, to account for that. Okay, so we have our time. We can take this time, and what we can do is we can multiply this. And we said we want to multiply our time by 2 pi and by f. So what we can do is we make a constant, and this constant here, we can press P again to open so we can see what we're doing actually. This one here by default is 0. But what we said, we want 2 and pi. We could make 2 constants, or we can make our life a little bit easier. We can just write here 2 times $pi. I could write 2 times 3.14 as well, but actually this it's like a value you can just grab from Houdini. It's a little bit more precise. It has a 5 digits instead of 2 behind the comma precision, so we can just use this value instead. So we can just plug us in here, and now we're taking the time and we're multiplying it by 6.28. I tried to explain before in the slides why this is the case, but I'm not sure if it really landed, so I'm going to try again. If we have a default sine wave, so let's say we have sine of t, it would take 6.28 seconds for one full sine wave to pass if we're just passing in the time like that. So if you would write just sine of t, it would take 6.2. Why? Because it takes 6.2 radians, and we will use this value, we'll see in a second, as radians to do one full circle. And one sine wave is nothing else than one full circle unrolled. Right? I showed this in the theory. It's basically just, instead of doing the circular motion, you're basically just doing it as in a wave motion. But we're still covering 360 degrees or 2 pi. To basically now speed up the process, because our frequency, what our frequency is trying to say is it's how many waves do we have in 1 second. So if we would have this as 1, we would have to go through 6.28 radians in 1 second, not through 1. If 1 second passes, we don't want 1 radian to go over, we want 6.28 radians to pass. We want it to basically be sped up by the factor 6.28. And because of that, we have to basically take here our conversion, and that's this 2 pi comes to trying to convert our sine wave that is just a sine wave into a sine wave that has a value called frequency, which is directly linked to how many waves do we have in 1 single second. And that's why this 2 pi comes in. Right? So just a conversion factor to trying to speed up the original sine wave by nearly 6.3 to make sure that it actually goes fast enough that it would happen once a second. And then if we then make it even faster by multiplying it by the frequency, we can then get even more sine waves. Yeah. So we can, like I said, we also want to multiply 2 pi times the time, but also here times the frequency. And it would be very annoying if you want to change something, if you always have to dive in here and change it in this network. So what we can do instead is we can create something called a parameter. And that parameter allows us to modify stuff outside of the network. I'll show in a second. But important is this name is really bad, because if we have lots of them, if this is named parm, right, it's going to be very unclear what this is. So let's call this what this is actually, and it was our frequency. And we can abbreviate this if you want, or you can write it out. It's not so important as long as we know what we're talking about. And then here, that's a very common mistake we see people make, is that make sure you don't pick this bottom value. This bottom value just means this bottom value means that you picked if this was bound or not. It's like a Boolean switch, but the actual value is here above. It's this one. So never, unless you know what you're doing really, never pick this bottom one. You always want the top one. And so now we can see here we're multiplying these in a random order, but it doesn't matter because it's multiplication. That's very important. We couldn't do this for division or subtraction. We would have to pay much more attention, right? But now what we have is we have 2 pi, which is this one, times f, which is this one, and we multiply it by the time. Great. One important thing though is our frequency here by default defaults to 0. That's very bad because multiplying by 0 makes everything 0. So we would see nothing happen. If we have a frequency of 0, which means we have no sine waves per second. So it's not that it's wrong. Mathematically, it still works out. It just means nothing moves because there is no waves anymore. So that's a bad idea, of course. So we should change here the float default value to 1, for example. And then don't forget, we now did this part. But inside of our sine, we still have to first now add this h. So this h was the horizontal shift. So we can make an add node, and we can make another parameter. And we can call this h for horizontal. And again, we can default this to 1 if you want. It's not super important. This one actually, because we're adding it, adding 0 is fine. So we could leave this at 0 as well. It's just with multiplication. If you multiply by 0, it kind of like breaks everything. So we can grab this here. And so where can I change these now? If I would go one level higher by clicking up here in my graph, I can actually now see these are added here. So I have frequency of 1 and a horizontal shift of 0. Yeah. Very important also, of course, we want to move our display flag here. So now our sphere is, the sphere that has been modified by the math is being displayed here. So now that we have this, we basically did all of this in the inside. And then we know we have to do the sine of it, right? Because we solved the brackets. So now the next is the sine. So we can do sine. And you can see here, it says radians. But like I tried to explain before, because of this is technically 2 pi radians, what we're doing here. So basically, we're multiplying the time we're putting in by 2 pi radians. And by doing so, we basically make sure that we have a correlation where this frequency value we're putting in now makes sense, that we get enough radians per time to basically either spin our circle or move our wave as fast as we want. Right? So this radians here is correct. If this wouldn't be correct, if it would say here degree, we actually have to be careful and we have to do some kind of conversion still as well, which, by the way, it's very easy. You can just say degree to radians or radian to degree. So it's never a problem, but it's something to just keep be aware of. But because it says here radians, we're completely fine because we are working here in radians. Okay, so now that we have this solved, we have to still figure out, do we first add the vertical offset or do we multiply? Multiplication trumps this, right? So that's important. So what we can do is we can multiply here. And we want to multiply by another parameter. And again, it's multiplication, so let's change the default value to 1. And then this one is our amplitude. And we can connect this here. And that's a lot of stuff to do, but we have one last step, and that's adding here our v. So you can say add another parameter, and that's our vertical. And this one again, because we're adding it, it being 0 is not a big problem. You could we're gonna change this anyway, however we want later on. But it's just something important to understand that, like, if you're multiplying a 0 as a default value, it usually just breaks your entire thing. So just keep this in mind a little bit. So now this is actually, this here is the result of this formula. And this formula, what we're actually doing is, we're saying our position that we want is this. And so the position that we're looking for gets calculated by all this math here. Which means that we can do is we can just grab this here. And that's the one thing I tried to say before, is we have one little problem still is, if we would put this now, like we said before, just into a position like this, we would move on both the x, y, and z axis, which is not ideal, right? Like we want to move up and down, not like diagonally. But you could use this, for example, in a game to move a platform diagonally. Or even you can move with unit circle, you can move a platform in circles. So all this math we're doing, by just tweaking it a little bit and overlaying one with another, you can make all kinds of, for example, like this is a great movement as well for like Mario style game platform. Because it has this you will see in a second, it has this very nice ease in and ease out of the animation. And that's because of the way that it flattens out on the graph of the sine wave. It's this here. It's not spiky. It actually has this nice smooth curve here, and that's why it looks so good to use it for animations and stuff like that. So what we can do is we can go here and we can make a vector from this. So now we don't vector. So we want to basically float to vector. So we don't let Houdini do this for us. We now do it manually. And then what we can do is we can check in Houdini, the up axis is the y axis. And you can see this here at the bottom left. If you check by yourself, it's always a bit difficult to show because it every time you move your mouse, it kind of like undoes it. But you can see here the green thing is the y. Yeah? So what I can do is I can just take this and plug this in only in the y. And you can see the other two just default here to 0, which means my vector here I'm getting out is 0, the stuff we calculated, 0. So I can put this in here, and you will see it actually moved a little bit already. And if I go here now, you can see it moves as well. And it's because by moving here on the slider, I'm actually now looking at different times. And because I give a different value in here, right? Because I give a different t in, I get a different sign. And now the cool thing is what the sign does is it basically gives it an upper, like a lower and upper limit. So if you look here, right, our graph, if this is the position, it can never get larger than 1, for example, and it can never get smaller than -1. But I can tweak this. I can say, okay, it can get larger, but I can very specifically control how much is this movement. So if I just press play now, you will see this moves pretty fast. Why is this? Because we're going, and you can see this here, normally we expect to go through 24 frames per second. But if you don't click on this little clock here, it just keeps going as quick as the PC can do, basically. So if your PC is better than mine, it would go even faster, right? So to limit this, we can just click here. Now, yeah, I have my double clicking happening. You can see this is basically now our sine wave we made. And you can see and if you would try to count it, because our, you can see here our frequency is 1. If you would try to count this would roughly now go up and down every second. So if you would 21, 22, 23. So this is actually really, you could use the clock if you wanted, as long as your simulation is running nicely. So what we can do now is we can actually tweak our frequency to show a bit how this changes our behavior. So if you understand what I said before, let's have a look here. If we change the frequency, which is basically the same as the pulsation, just with a conversion factor, right? But the behavior is the same. If we give more pulsation, we give more frequency, so a higher value, we get more waves. What does the wave mean? The wave is showing to go through one full motion. So if we have more waves, we go through more motion at the same time, which means it goes faster. So let's try this. So if we put this to 10, you'll see it actually becomes difficult to see because now it's moving 5 times per second. So if I put this to maybe something like 2, you can see now it goes twice as fast. Easy to see if I put this to like 0.5. You will see now it moves, and you can see now slowly you can start really appreciating this motion. It's like, it's not going like stop fast, like it doesn't kind of like stop at the top, but it really slows down. And the other value we had, we could say, we can use the amplitude. I'll show you again how this looks here. We can use the amplitude to make this a larger value here, right? So it's multiplied here in the beginning. For us, we multiplied it after doing the, we multiplied it here, right? This is our amplitude. To be very clear, we are doing the exact same math here as written there. It's just in notes, right? But this is just a formula. And what you can do is we can increase the amplitude. Just say that's like 5, and you will see now it moves much further. And now you can really start seeing this motion, this like very elegant of the motion. If this ever happens to you, by the way, I did like a typo and it kind of ruined the line here. It's now always blue. It's because I used like a non-number, so it thought I was trying to do some kind of coding in it. So to undo this, you can just right click and say delete channels, and then it gets rid of it. But you can see now how this moves nicely, right? It moves, and it moves from 5, from 10 to -10. Right? If I move this back to, if I move my amplitude, if I want to shift this up, I can use the vertical. Wait. It's probably just not enough at the moment. Let's put this to 10 as well. And yeah, that's what I wanted to show. It's like now we can see, and it's a bit, maybe if I go into the, let's go into one of the views. So you can click here on perspective and then go to front view. You can see here, and you can see we're going from 0 to 20 actually now. This is 20. So that's something very important. It's a bit, sadly, it doesn't show them here. If you happen to have your amplitude the same as your vertical offset, it just happens to be that it always ends up exactly at 0. And that actually holds up here as well. If it's very difficult for me to do, of course, but if my amplitude, so here my amplitude, so I have here 3.1 from amplitude, and my vertical offset, if I put this also 3.1, you will see that these actually here start touching. They're exactly here on 0. Right? Okay, so let's change this now to an actual spaceship. So how can we do this? What we can do is we can go in here and we can make a file node. And now comes this where I'm not sure if we're going to try to share this with you. It's might be a bit difficult. But you can just model one quickly yourself, or you find it can be any object you want. That's the important thing I want to make you understand. Like, this is just a mesh we're going to use now. You can put anything you want in here as long as it's a file you can import into Houdini. Or you could even make something here in Houdini, right? As long as you plug this into our math node, this will work fine. So what we can do here with our file, we can just import here quickly. So I'll select here with the, let's not close our file here. Yeah, that's always a good idea. Let's just save this quickly before something crashes and we lose this all. We haven't saved it all yet. I'll quickly just put on my desktop. but just so we have a save file somewhere. But I can now pick here on the right, I can pick from where I want to do this. I can go to my desktop and I have here my land speeder FBX. And you can see this is the model we have, right? So it looks something like this. It's quite big. I think it was made in 3ds Max. And yeah, it's basically 1 unit and max is 1 centimeter, while in Houdini it's a meter. So this is gigantic at the moment. But basically this means now if we put in stuff here, they are now not meters anymore, but centimeters. So just keep this in mind. What we can do now is we can just plug this node in here. And you will see that if we now visualize it, it disappears again. And that's for the same reason that I showed here, right? With the box, while here our box is each point is somewhere else. If you override the position of each box, because this loop actually, it goes over every single point. And here you can see the single points, and if I put them all in the same place, it will be a problem. But if I pack it, then now this mesh with lots of points gets replaced with a single point. And of course, you could just add, you could do it as an offset instead. You could just do a little bit different math by just adding it, but I want to keep it simple for today. So we can do is we can just pack this as well. So just add a pack node, and now you can see we have here our yeah, if you press F, by the way, it frames the object you have currently selected. So if you just press F here, it, while being on the left in your viewport, it should frame this. And now you can see here is our point that it uses. And if I press play, you will see that it now nicely goes up and down. And that's because our packing, I think, packs the center. Yeah, we can also just pack origin. And then you can see it now actually works much better. It really depends which mesh you have, right? But now we have this nice motion, and what's the interesting thing is now we could have animated this very easily with a curve as well, right? But what is much more difficult then is, what if you want to change this? What if you want to make this go much faster? We could put this go super quick, right? This is of course way too fast, but we could have this, for example, hovering quicker or a little bit quicker. And you could do this in a game. You could just do this, for example, maybe a certain property or so makes this go faster. You could put this much slower as well, where it's really just very, maybe just standing around, it's just kind of hovering slowly in the background. So you could tweak this. And also important is we could change still how high this goes. We can put our amplitude, we can just change the offset. This means now it will hover further above the ground, but it still moves the same amount. But if I increase this one now as well, now it will also move more. So I could actually make this go like way more, right? And then now it will also clip into the ground though. See, it goes into the ground. So I should probably put my vertical offset also a bit higher. Let's say 110. And see now it's like, but now it's going way too much, right? But the nice thing is we can just tweak this a little bit. We can adjust it. Yeah, with middle mouse click here, you get this setting here where you can really just, and we can just make this larger and larger. We can say this is the average we want to hover around, basically. So I can move this down. So, and I can really fine tune now exactly. So for example, let's put the frequency back to 1. And we maybe have something like this, right? So now I showed before, so you can use some flickering. And also in the PowerPoint slides I mentioned, so one of the first examples that we actually can use this kind of math to make like a screen animation, stuff like that. So how does this work? It's actually surprisingly simple. The only thing I have to make now is I have to quickly make a sphere here. Or we can actually use the one that we had. And in Houdini, you can just move your, you can have your display flag like this, right? But you can also move something called a template flag. And that's kind of like to show you like, to show this node to you as a wireframe while you're on another node. So what we can do is we can now be here on our sphere, which is this tiny thing here at the bottom. Let's pause this. And our goal would be to have this here adjusted to the right, right? So let's make this a bit larger, and let's try to really, and let's maybe move our display flag before the pack node here, because this is already being moved here now by our thing, right? So we have our little sphere. What we can do is we can take our sphere and we can just make it a little bit larger. Let's make this even larger. Something like this, and then we can actually take the center and we can just try to move it up so it kind of like ends up where our engine is, right? You could of course also like work with proper selections and so on, but again, it's about like demonstrating the principles today, not about like 100% how to work in Houdini itself. Let me make this a bit less. So let's just say we do something like this, right? And now what we can do is we can take this node here and we can merge these two together, actually. So there's a merge node. What does this do? It basically takes this sphere and includes the sphere into the file heap. And you can see that now if I move this, they actually move together. Why do they move together? Because I put them together here and then I'm moving whatever the result is, right? But having this separate here now allows us to actually animate this and to animate the color. And to quickly show you how simple this is, we can actually take this node, we can just paste this because the math, and that's the important thing, the math is exactly the same. So what we can do is we can take this here, we drag this in here, and we rename this, of course. So we're going to call this math underscore flickering light. And we can cut this one here away, otherwise it will merge it in again, and we can connect it like this. So important now is, of course, what we're doing now here doesn't make sense because now we're moving this guy, and then we're moving it, then we're merging it, and then we're moving it again. So now it would kind of like move here weirdly, right? This doesn't really make sense. What we do want to do is we want to change this one here to not affect the position, but the color instead. And if you know anything about pixels and so on, then you know that color is usually RGB, right? You have red, green, blue. So if you want this to be red, all we have to do is just plug this in here. So this would be now red and then 0, 0. So we would now make a color that has whatever we calculate in the red channel, and then in the green and the blue we'll have 0. Of course, important here now is that we do not want to connect this here to the position anymore, but instead this should be connected to the color. And you can see now this now starts glowing bright red. So all I changed is I just took the exact same math we did and I put it into a different, and we could even leave it. The difference then now would be that it would be green instead now. But it made a bit more sense for us to make it red, so we can put it in the first one. But now we have this value here, which we can change, right? And if you look at our graph here, what would we want our value? So red, green, and blue usually are values between 0 and 1. So what we can do is we can change our sine wave in a way where we actually move it around 0.5 with the amplitude 0.5 as well. And by doing so, you'll see that our actual value never becomes negative here. It would never become blacker than black because a negative color doesn't make any sense for Houdini. So we'll just make it black. But the problem would be if we do this, that we would have like periods of full black that just go for a while. And if you're larger than 1, it would get like really, really bright red like we have now. So we can make a sine wave that is exactly, and that's kind of when it becomes important that you understand how you can control this. We need a vertical shift of 0.5 and an amplitude of 0.5 as well. And I'm trying to like block it in here, right? It's a bit difficult, but you can see a 0.5, 0.5. Now it really nicely matches here. It goes from 1 to 0. And that's something we also teach in our course, like how do you exactly control these values by understanding the math behind it? Because at the moment we can just play around, right? We could just change this and we could say, okay, let's just have a look only at this this red sphere here, right? Let's have a look at this. We can see you can see very little actually here, right? Why is it? Because our amplitude is too high, and but I can move this. See now it becomes on off, but it looks a bit weird. If I know now that I set this up correctly from 0.5 and 0.5, and see now we get this very it never is black for a long time. If you want this, you could do this, of course. Right? You could, for example, have, see now it stays black for a bit. If I make this even less, I could just stay black for longer, right? I can basically modulate exactly how this sine wave shifts this color value. But if I know what I'm doing, I would say, okay, I probably want this both to be 0.5, and then I get a nice value that always goes from 1 to 0 and back to 1 and back to 0 and so on. I can horizontally shift this. It doesn't really do much. It just changes the starting value. So you can see if I would be at 0, or by changing this, I would decide if it's red or not. But in the end, it would do the exact same behavior, but I can, for example, change if I want it to be off or on at the beginning by shifting it. Because it either will start at 0 or start at 1 or anything in between. And now the frequency is important though. With the frequency, we can change how fast this dims up and down. So with 4, for example, it really starts flickering now, right? We have now 4 times it goes on, off, and then on, off, and so on. And if you make this way too high, of course, it doesn't really, it still does more now. It's just, you just can't see it. It's just, you don't have enough frames in your, but if you would do this one, for example, it would do like a really slow fade. So this could be cool for like a warning, you know, like these pulsing, like for example, you have like a submarine game and you want your lights to go on and off and so on. And yes, you could animate this, but doing it like this, you really have much more control of tweaking it very quickly. I could put this again to 3. You can see you have this nice flickering. So it's the exact same math. We're just using it for something different. That's the really important thing to understand. Yeah. So if we now combine this, we get basically our end result, which is our hover vehicle, which is flickering and moving at the same time, and we can change everything. Okay? So that's basically what I wanted to show for you guys today. I hope it wasn't way too much, because it's quite difficult to pick one topic, and because you're missing the introduction to Houdini, you're missing a bit of the background for math. So I hope it was still clear enough to follow. We take much more time to also introduce the software and so on for our students usually. So if you have absolutely no Houdini knowledge, maybe come back at some point when you're a bit more comfortable, because it's really something that once you get used to this, you can do a lot of stuff with it. And I want to really give a shout out to another video on our YouTube channel. We made about half a year ago, plus minus, we made a video for an event of SideFX, of the company that makes Houdini, where we showed a bit our course. And in there, we had a much bigger, we had much more time to edit everything and film and so on. So we have really like a walkthrough of way more stuff that we cover in the course. So it could give you some more ideas of what to do. And there's another demonstration where I actually walk through some shader math and show you how you can, for example, actually how you can understand how your engine actually, how game models get and film, how stuff gets lit, like how stuff gets rendered out, how you basically can decide what is where there's color and where there isn't, and how you can, for example, do like an outline effect and stuff like that. Yeah, so if you're interested in this, definitely feel free to check out more. And if you have any questions, I'm gladly going to help out in the comment section. It's just very difficult we're gonna have so many different levels of people who, this explanation here in the beginning, they will not understand why anybody will have to explain this to somebody who can find their way around YouTube, while there's other people who probably for this is incredibly difficult. What I want to show you is, and that's kind of really the takeaway of today is, yes, math can be sometimes tricky. And yes, if you look at this, it can look very mathematical. And you can see what we do other stuff. We do vector calculations, we do trigonometry. But we always do it because if you understand it, it gives you power that you can use somewhere else. And you don't use it to solve these equations, but you use it for stuff like this. You use it for calculating lighting, for placing stuff, for calculating, using vectors. You can calculate how to turn certain things to make sure that you have, like, in your procedural asset, you can turn all your normals around to make sure that you align stuff nicely and so on. So it's really the reason we teach our students math, and why I think any artist should really learn math is not for the sake of math. You had math in school for that. You understand why math, everybody needs some math, but a lot of people don't understand that actually knowing some math as an artist can be an incredible boon to yourself. And if you actually start looking around, you will see this. You will find math courses for artists. You will find for all kinds of like similar positions, like Unreal Engine made a great 2-hour podcast where they also showed some stuff like how can you use some vector math to calculate light beams and reflections for like some puzzle games and stuff like that. So they really knowing math, think of it as like that. It's like, yes, you do not need a mouse to do 3D. You could very much use your keyboard and you could try it, and it would be incredibly painful. but you could do it. Or you could maybe the other way around. You don't need a keyboard to do. I could always go here and I can click on stuff and I can use these buttons and I can select stuff. Right? I could like slowly work my way through stuff instead of going and using the keyboard shortcuts. I could do this, but it's just incredibly tedious. And it's the same with math. You often don't need math. I could animate this by hand, but if I know how to do it right, then I have the option. I can say, you know what, I can just do this by selecting stuff. I'm doing it like manually, or I understand how I can use math, often with a bit of coding, to automate the process, to understand that I can, for example, automatically calculate in which direction a tower has to look like based on what I'm doing, right? So it's the math gives you one extra tool set. And while it's definitely not impossible to do any of this without math, having the extra math, and even if it's really as simple as taking a sine wave and converting it, or to make a flickering screen in the game, don't shy away from it. It's math always looks difficult till you slowly start using it, and then all of a sudden, actually often it's not nearly as complicated. It's just the way that math gets written down that can make it very difficult. And I think that's really important to understand, is that like you can find really, really cool, and we have lots of examples in the other videos. So if you want to see a bit more like some concrete stuff I'm talking about, like you can make like flower patterns using stuff. You use like Lissajous curves to do all kinds of crazy things. And the math in the beginning, you always look at it and it's like, this looks very difficult. But the point is, you don't have to prove that it works. Somebody did this for you, often hundreds of years ago. You just have to understand, how can I use it in my work, right? And that's the really important part, is like just try to stop being afraid of math, and every once in a while see if you can use it a little bit and understand it. And I think it will make you much more complete as an artist in the end. Yeah. So that's it for today, and I hope you could follow along a bit. And if you have any questions, please put them in the comments and we'll gladly help you out. Okay, bye-bye.